Hello and welcome to Unit 7. In Unit 7, we'll begin by learning one way of multiplying vectors together. And this method is known as the dot product or sometimes as the scalar product. So what is it? Well, as I said, it is a way of multiplying vectors. And this particular way of multiplying vectors results in a scalar, thus why it is called the scalar product. The dot product in a lot of ways is indicative of how parallel two vectors are to each other. Now you may be wondering, why is it called a dot product? And that's because of the notation that is used. So if I want to take the dot product or the scalar product of two vectors, I write in the first vector, put a dot in between, and the second vector. So this is A dot B. Properties of dot products for unit vectors. Okay. If you take a dot product of any unit vector with itself, you get 1, indicating that they are perfectly parallel to each other. If you get a value of -1, that means that they are exactly opposite each other. On the other hand, if you take the dot product of any unit vector with any other unit vector, you get 0. So I dot j is 0, j dot k equals 0, and I dot k equals 0. Okay. Well, it's fine to know what you have with unit vectors. So how do you calculate the dot product of any two vectors? Sorry, one slide too far there. If I have a vector A, which I can write as an x component in the I hat direction, plus a y component in the j hat direction, plus a z component in the k hat direction. And similarly, I have a vector B with its components. Then I can take A dot B. And you might imagine that you get something that looks like AX I hat dot BX I hat plus AX J hat. Nope, that is an I again. Sorry, AX I hat dot BY J hat plus AX K hat dot BZ K hat. And we could continue on. But if you look, any term that involves I and j, so the x component with the y component, this one goes to 0, as does this one. In fact, every term would go to 0 except the ones for the same components. Okay. But as we just learned on the last slide, I hat has a value of 1, and j hat has a value of 1, and k hat has a value of 1. So this ends up being just ax bx plus ay by plus az bz, and that is the value of arbitrary vectors a dot b. Another way you can think about this is by considering, what do these components look like? So here I have two vectors, A and B, defined in a coordinate system. And we can see that A will equal AX I hat only. B will have two components, know the magnitude of B, I can find what these components are in terms of the angle theta. So that would be B cosine theta I hat plus B sine theta j hat, as I have it written and drawn here. Okay, now if I take A dot B, I get AX BX, but that equals A B cosine of theta. So in general, I can write A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between them. Couple of properties of dot products. It is commutative. If I take A dot B, that is the same as taking B dot A. It is also distributive. So A dot B plus C equals A dot B plus A dot C. And that is the basics of the dot product. Before we finish, I would like to work an example with you. So here I have a vector A, which is 4I hat minus 6J hat, and the vector B, which is 2I hat plus 2J hat. So if I want to find A dot B, I'm going to take the X components and multiply them together. So that will be 4 times 2. And then I'm going to take the Y components and multiply them together. That would be negative 6 times 2. Okay. Well, 8 minus 12 works out to be negative 4. I can ask, what angle does A make with respect to B? Okay. Well, I know that I can write A dot B equal to the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between them. Okay. Well, that means I need the magnitudes. So to find the magnitude of A, it would be the square root of 4 squared plus 6 squared, or plus negative 6 squared if you want to do it that way. And that works out to be 7.21. And I can find the magnitude of B by taking 2 squared plus 2 squared, and that works out to be 2.83. So now I can come down here and say negative 4 equals 7.21 times 2.83 times the cosine of the angle. That results in the cosine equaling negative 0.196. Taking the inverse cosine gives me theta equals 101.3 degrees. Does this make sense for an answer? To look at that, I'm going to graph these two vectors, my y-axis and my x-axis. 1, 2, 3, 4. I'm going to need a little bit more length there. 1, 2, 3, 4, 5, 6. Okay, so down here at 4, negative 6 is the vector A, and the vector B is up at 2, 2. Okay. So let's think about the angles. The answer I just got was that this angle from A to B, or B to A, it doesn't matter, is 101.3 degrees. Does that angle make sense? The best way to answer if that angle makes sense is to answer the next question on the slide. And that question was, what angle does A make with respect to the x-axis? We know B as a vector 2, 2 makes an angle of 45 degrees. So we know that this part has to be 45 degrees because B has components 2 and 2, which makes it a 45-degree triangle. So what angle does A make with respect to the x-axis? So in order to find that, I'm going to take A dot I hat, because I hat is a unit vector, length 1, parallel to the I-axis, or to the I-axis, the x-axis. That will be the magnitude of A times the magnitude of I times the cosine between A and I, or A and the x-axis. Okay. Well, A dot I will result in a value of 4, because the x component of A is 4. The magnitude of A we just found was 7.21. The magnitude of I is 1, so I'll put that in. And then we have the cosine of the angle between A and I, or A and the x-axis. Working that out gives that this angle is 56.3 degrees. So that would be from the x-axis down to A, 56.3 degrees. 56.3 plus 45 is indeed 101.3 degrees. This concludes this portion of Unit 7.